Mr. Heffron here, and here's a video on force fields with centripetal motion. So as you can see, we got ions hitting the Earth's magnetic field and then traveling a circular path. Electron orbiting a proton, which doesn't really happen that way. And we got a satellite over here. Here we got some electrons orbiting a nucleus, and we got planets orbiting a star. Of course, the star is kind of turning at the same rate as the planets. Kind of silly. So, centripetal motion. Recall, centripetal motion is circular motion at a constant speed. One or more forces continually redirect the object into a circular path. The overall centripetal force acts towards the center of the circle and is perpendicular to the tangential instantaneous velocity vector. So the velocity, for example, is forward here, but the centripetal force is perpendicular 90 degrees to the center. And then as you follow the circular path, now the instantaneous velocity vector, which is tangent to the circle, so it's tangential, is traveling down, and the frictional force providing the centripetal force is towards the center. So usually most people say towards the center is the negative c hat direction, and outwards is the positive c hat direction. So we had Newton's second law here, F equals ma, but for centripetal motion. And there are three formulas you can use for centripetal acceleration. There's, let's see, v squared over r, 4 pi squared r f squared, and 4 pi squared r over t squared. So we're going to look at how different force fields are used in centripetal motion. So gravity is used for planetary motion and for satellite motion. So here we got F equals ma. So now here's the moon. The moon has a mass of 7.35 times 10 to the 22 kilos. Its orbital radius is 384,000 kilometers from the Earth, center to center. And of course the Earth has a mass of 5.98 times 10 to the 24. So the centripetal motion is going to be provided by the force of gravity. So we got negative gmm over r squared. And on the other side, if we want to find out how fast the moon is traveling, we have m negative v squared over r. So the r cancels with the square over here. The little m's cancel, so it doesn't actually matter what the mass of the moon is. It could be smaller, bigger, it doesn't matter. It would have the same orbital speed. And so when you rewrite it, you get this nice little handy formula for orbits. Orbital speed is always just the square root of gm over r. So in this case, 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 over 3.84 times 10 to the 8. And so the moon is moving through space at 1,019 meters per second, or just over 1 kilometer per second. So from Barry to Toronto, it'd be like 95 seconds at that rate, or around Mach 3. Okay. So according to many sources, the radius of the first orbital shell in a hydrogen atom is called a Bohr radius, and it has a value of 5.29 times 10 to the negative 11 meters. So supposedly this is where an electron is on average in the first orbit around a hydrogen atom, which is just a proton. So find the frequency of the electron in the orbit. So how quickly is this thing making circles? So we can find out. So in this case, we're not using gravity. The gravitational force is way too small to matter here. It's going to be the electric force, which is like 10 to the 20 times more forceful. So we get kqq over r squared, m negative 4 pi squared r f squared. So we're using the frequency formula. And the charge of the proton is positive 1 elementary charge. The charge of the electron is negative 1 elementary charge. So we're going to get ke squared here. And then the minus from the electron and the minus from the centripetal motion cancel out. And we get 4 pi squared m r cubed f squared. And then all we have to do is divide everything over to the other side. And then square root. And we can simplify the equation a little bit. So we have the square root of an e squared. So we get an e on the outside. We get 4 pi squared, which when we square it is 2 pi. So we get e over 2 pi times the square root of k over mr cubed. So for a hydrogen atom, the elementary charge is 1.6 times 10 to the negative 19 coulombs over 2 pi. The The constant is 9 times 10 to the 9. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. And the Bohr radius is 5.29 times 10 to the negative 11 meters, which we're going to cube. And so we get this frequency, 6.58 times 10 to the 15 hertz, or 6.58 petahertz. If you look up what frequency of light that would make, that's similar to ultraviolet radiation, which is anywhere from 0.75 petahertz to 30 petahertz. Of course, the Bohr model, the solar system analogy of an atom, isn't really accurate. Really, you should be using quantum physics, but it is a fun little physics type of problem for fun. Okay. The third type of centripetal motion that occurs is when an ion, a charged particle, runs into a magnetic force field at a perpendicular 90-degree angle to its velocity vector. So for example, over here I got an electron running into a magnetic smoke box trap that particle physicists use. And so this electron runs in, there's all the smoke here so we can see the trail, and it goes in, and the magnetic force is from the North Pole to the South Pole up. The electron's moving forward or right through the trap, and it's going to get stuck, and it's going to travel around in a circle, and it probably will run into some particles or ions on the way and slow down and spiral inwards eventually until it stops. So this is what it looks like. From top view, it looks like this. The electron's moving at a velocity v. We got magnetic force field lines coming up, and so we're going to have a magnetic force towards the middle of the trap right there. Okay, so centripetal motion is going to be the magnetic force, which is q v cross b. So the cross product of the velocity and the magnetic force field, which is just qvb sine theta, but it's 90 degrees, and sine 90 is just a 1, so we'll ignore that. So we're going to get minus, I forgot the minus sign there because it's a negative force. It's causing motion towards the middle, so I put the minus sign down here. So we get minus qvb equals m negative v squared over r. And so if you want to find out what the radius is going to be, you just rearrange that. You get mv, which is technically momentum, divided by qb, charge times magnetic field. And so the radius would be 9.11 times 10 to the negative 31 kilograms times the 10,000 meters per second that we have the electron coming in at, divided by the charge of an electron, 1.6 times 10 to the negative 19 coulombs. That's just one elementary charge. And we have a 1 microtesla field, which is 0.000001 Tesla. So that would make circles with radii 0.057 meters or 5.7 centimeters. It would be visible to the naked eye. So physicists actually do this when they're studying charge to mass ratio. They shoot a stream of particles into a magnetic trap, measure the radius, and with that they can measure the charge to mass ratio, the ratio of m over q. Okay, what if the ion is not moving perpendicular? Or parallel to a magnetic field. So if it's moving parallel, there's no deflection. If it is moving perpendicular, it's trapped in a circle. But any angle between 0 and 90 causes a corkscrew spiral or a helix type motion. So for example, let's get a proton inside a 1 millitesla field, moving at 10 to the 6 meters per second, forward 30 degrees right of the magnetic field. So here's the proton, and between the magnetic field lines, there's a 30-degree angle right here. So first you have to do is find the centripetal and tangential vector components. So perpendicular component would be 10 to the 6 sine 30 degrees, or 5 times 10 to the 5. This is going to cause the circular motion. And then the undeflected portion is going to be 10 to the 6 times cos 30, or 8.66 times 10 to the 5 meters per second, approximately. Okay. So for the centripetal motion, we're going to get qv cross b. So with our 90 degree right there, and we can find out what the radius is going to be. So it's going to be 10.4 meters. Okay. And oh man, okay, so I just noticed a tiny typo there. I just said 10 to the 6. It should have been 5 times 10 to the 5. So I fixed that. So the radius is going to be 5.2 meters. Okay, so the circles are going to spiral with a radius of 5.2 meters. I'll just fix that down here, 5.2 meters. Okay. And it'll be moving forward at 866,000 meters per second. Okay, there we go. Oops. There we go, so 5.2 meters. Okay, so in summary, centripetal motion occurs with planets via gravity force, and theoretically with the Bohr model of the atom via the electric force. And of course, the magnetic force fields can also cause centripetal motion with ions. So here we got gravitational. So for example, a planet attracted to a star or a satellite attracted to a planet can move in a circle, just like down here. Theoretically, although not realistically, the Bohr model of an atom, which kind of looks like a solar system. There you go. And when ions do hit magnetic fields, if it's perpendicular, they get 90 degrees motion. If it's parallel, no deflection. And if it's anywhere between 0 and 90, like this one here, then they travel in a helix or spiral. And this is actually what happens when solar radiation hits the Earth's magnetic field. Positive ions will go one way, negative the other, and they form circles in the atmosphere, which then gives us the light shows, the aurora borealis and the aurora australis. So I hope this has been useful information for you, and good luck on your work.